About kinetics of radioactive decay. Um, the kinetics would refer to how fast reactions happen or any process, any chemical process. And in our case, when we talk about velocity of a chemical reaction, we call it the rate of reaction. And what we're interested in typically is looking at how the concentration of the reactants change over time, or how the number of particles of specific chemicals change over time. That's what we call kinetics in chemistry. And we also like looking at the different factors that may affect the rate of the reaction, the speed of the reaction, how fast the reaction happens. In this case, we're going to talk we're going to do a full chapter on kinetics later in the semester, but now we're going to refer only to a very specific type of kinetics that pertains to decay, nuclear decay. So a couple of things that make this more intuitive is when we look at the actual event phenomenon that occurs when a nuclide decomposes. Since we have the decomposition, remember from your studying of the different types of reactions, decomposition, we take something and we go from one thing to more than one thing on the reactants, on the product side. So when something decomposes, spontaneously, that one thing just reacts. Okay, it doesn't have to collide with another chemical, so it does not depend on the concentration of another chemical. And intuitively, we would think that the more particles that we have, the more reactions that will occur. In this case, decompositions or decay processes. So the more we have, the more decay events, which means the faster the sample will decay, or the more particles will change per unit time. Here we have two containers to represent that, and some of what I want to do here is like, I think it's like model the way that you can learn from reading your textbook when you come across pictures, images, figures, diagrams. So if you're given like these two containers, A and B, they contain uranium-238, both of them, and you can interrogate, you can question that information that's been presented to you. And you can think, okay, in which of these two containers would the reaction happen faster, A or B? Understanding that we're talking about decay processes, that is spontaneous decomposition. Most probably you would say the reaction would occur faster in the one that has more particles. And that is the same as saying the rate of decay is going to be greater for container A. Now, there's one thing that's very important here to clarify, because some students I've noticed get a little bit confused about this. When we have a collection of particles, like here uranium-238, and we talk about them decomposing, they are not individually decomposing at the same time. You can find an average of the time it takes to decompose a given sample. But it could be that this one particle up here stays there unreacted for a very long period of time, whereas the one next to it reacts very quickly. So the particles are reacting, are decaying individually. So individually they will decay at different times. How many particles react per unit of time is what makes what we call the rate. So try to keep that in mind. When we talk about the rate of the reaction, we don't imply that all of the particles are reacting at the same time. So if we understand from this diagram here that the more particles we have, the faster the rate of the reaction, we can say that the rate is proportional to the number of particles we have. In this case, the particles are the nuclei, the particles are the isotopes, the particles are the nuclides. Okay, I prefer the word particles. So they are directly proportional, which means we can make that proportionality an equality if we multiply n times a constant, which will be the proportionality constant. In this case, since we have a rate, we're going to call it the rate constant. So the rate, how fast the reaction happens, how many particles decay per unit of time, will be equal to a constant that's characteristic of the particle, like uranium-238, times the number of particles that we have. So K is a constant for the substance, for the particle. We have different ways to express that. We use this triangle, which is a capital delta in Greek, and in the Greek alphabet, and we use it to symbolize change. So the change in the number of particles for a given time will be equal to the rate. How many particles change in a given time? And we have a minus here because the particles are being decomposed, they're being transformed into something else, which means the number will decrease, and that's why we have a negative here. And we do a little bit of manipulations, mathematical manipulations that we don't need to completely fully understand at this time, that lead us to this equation we've got down here. The natural log of the ratio of n over n sub 0 will be equal to minus k times t. N is the number of particles, and this one here would correspond to the number of particles at time t. And n sub 0 would be the number of particles at time 0. K is the rate constant. We refer to this type of kinetics as first order, and by that what we mean is that the rate is directly proportional to the concentration or number of particles that we have. They're directly proportional. And that's where the first order comes from. Okay, so we established that just from the example we had with the two containers. The more particles we have, the faster the reaction will happen because it's a spontaneous decomposition. And here we have this other equation that we can derive from doing a little bit of math, which relates the ratio of particles that are unreacted, particles that are left unreacted, over the number of particles that were originally in the sample. It relates the natural log of that ratio to the time that has passed. Let's look at this plot here and see what information we can gain or draw from this graphical representation. We have, as always, we'll look at the axis and what is given. We have percentage of cobalt-60 remaining. Percentage would be the number of particles that are still unreacted over the original number of particles times 100 to make it a percentage. And we have the time on the x-axis. We have the nuclear reaction up here. We have cobalt-60 decaying, and we see that it is a beta decay. It also emits energy as gamma rays, and it is converted into nickel-60. So that's our reaction, our nuclear reaction. What does this plot tell us? Let me see. We've got 100% here. And if we look at the plot, we see we go down here and we see that this point right here corresponds to 50%. So that's when we have 50% of the material left unreacted. Obviously, we have 50% of the material reacted too, and that is corresponding to a time of 5.27 years. If we come back 5.27 years later, we realize that we have 25% of the material left unreacted. So between this point here and this point here, we have 5.27 years. If we come back 5.27 years later, we see that we have 12.5% left, and so on. So what this is telling us is that it takes every single time, it's taking exactly the same time to drop the original concentration to 1/2 of what it was. Okay, going from 100 to 50 took 5.27 years. Going from 50 to 25, it took 5.27 years. Going from 25 to 12.5, it took 5.27 years. So that time is a constant, and we call that time the half-life of the reaction. Half-life would be a time, and that would be defined as the time that's required for the number of nuclides to reach 1/2 of the original value. It is a constant, and it is related to the rate constant. Half-life, T1/2, equals the natural log of 2 over K. You can look at your book and see where that comes from, this natural log of 2. And that would take the value of 0.693. And we see that if we have one, we can get the other easily. For cobalt-60, we know from this plot the half-life, that would be 5.27 years. So we can solve this equation for the constant. And this is the constant, rate constant for cobalt-60. It is specific characteristic, it will not change. It's unique for cobalt-60, and we see that it has reciprocal time units, years to the negative first. We can also have it in reciprocal seconds, reciprocal minutes. Okay, now stop and practice. We've got a few exercises here. We're going to look at this plot and find from the plot the half-life, and then we're going to predict how long it would take for the number of nuclei to be 1/4 of the original amount, from going from here to 1/4. So you can count the squares, find the half-life, and evidently if the half-life is the time it takes to go from 1 to 1/2, if we wanted to go from 1 to 1/4, we would think that it would take how many half-lives? Good. Here we complete this table, which is just testing that you can divide or multiply, I guess. But also, you will have to predict the type of decay. You can go back to the plot we saw before for the band of stability and see where those two fall in that plot, and see what needs to happen to the neutrons and protons and predict the type of decay that would occur. And here, this is a reminder that for you to discuss or think, ponder about what I said, that even though we may have a half-life for carbon-14 of 5,730 years, that doesn't necessarily mean that every single individual atom is going to react at the same time, or that all of them are going to have reacted by that time, 5,730 years. Okay, they will react at different times, and that's something that we need to understand clearly. And then we're going to explain why these three equations are equivalent. This is important for you to understand later problems. In next video, we're going to talk about nuclear transformations.